All right, hello everyone. So this lab will be pertaining to the iron thiocyanate equilibrium experiment. It's called Chatlier principle, so you can see that in your lab handout sheet. So this is your pre-lab lecture for this particular experiment. And so we're going to go over what to expect in this lab, how to go about solving for the equilibrium constant, because in the end your goal is we're going to study the reaction between iron and thiocyanate. And when these two react together, what they're going to do is they're going to form this complex here. And so this solution here, when you look at it in a bottle or a beaker, it has a very, very light yellow color to it. This solution is colorless, but when you mix them together, the product is this really blood red complex that forms from this. And so we're going to use that to our advantage, because our goal is to solve for the equilibrium constant, but to help us to determine this, what we're going to do is we're going to use what is a technique that's called spectroscopy. In spectroscopy, what we do is we take a light and we pass this light through a solution. And so, as we all know, if you go to the restaurant and you get yourself a glass of sweet tea, it always comes out with ice. And so in the beginning of your meal, the color of your solution is really dark brown, but then by the end of the meal, a lot of that ice has melted, has diluted the solution, and now you have a lighter color. So as the light passes through the solution, that light will interact with what is in the solution, and so the concentration that you see is related to the absorbance that's detected on the other side. Now this absorbance is related back to Beer's law, and Beer's law tells us that absorbance is equal to the molar absorptivity, the path length, and the concentration. Now these two here, they're represented as constants. They're dependent on the solution that you're studying, but the absorbance and concentration are directly related to each other. As you change the concentration, you will change the absorbance. Thus the reason why you see differences in the colors from being that really dark brown to that really light brown color at the end of the meal. Now, in our case, we're going to use a spectrometer, and the wavelength we're going to be focusing on is 450, and that's because of the color of this solution that it makes. Like I said, it forms a really dark red-brown color. Now, after we've gone through the process and the experiment, we've analyzed the samples with a spectrometer. What we'll do is we'll set up what is called a calibration curve. And in the calibration curve, you're going to be looking at two different solutions. You'll be looking at the reference solution, and then you'll also be looking at the test solution. Again, these are found in the lab manual. So you'll have 5 different reference solutions, and those are what you're actually going to make a plot of. So you're going to form what is called a calibration curve, and you're going to plot absorbance versus the concentration of just the reference solutions themselves. All right, now in order to determine the concentrations that you go on the bottom here, what we have to do is we have to look at the actual molarities for the reference solutions. So you have 2 different solutions you're going to work with. You have a 0.2 molar iron plus 3, and you have the 0.0002 molar thiocyanate. Now, if you look back up here, that's a 1-to-1 ratio for these two reactants, but the way the concentrations are set, this 0.002 molar solution is going to, for the thiocyanate, this is going to be acting as your limiting reagent. And so for that's important, because this graph is basically representing the concentration of the FeSCN 2+ at equilibrium. And so if we had kept the concentrations the same, well, we couldn't do this graph. It wouldn't be doable. And so what we're going to do is we're going to use M1V1 equals M2V2 to solve for these concentrations here. So now you have to look at the actual procedure, and you look at the table 1. So what we're focusing on is the SCN minus. So the concentration of the SCN is 0.002 molar. The volume for the first solution is 2 milliliters. And so we're trying to solve for M2. Now V2 is going to be a total of 10, and that's the way it's always going to be in this experiment. You have that we're going to keep the total volume constant at 10 milliliters. And so now we'll solve for M2 here. All right, so just multiply these across and divide by the 10. And what you'll end up with is 4.0 times 10 to the negative 5 molar for that first solution. And so what you'll do is you'll calculate the concentrations for the other 4. So there are 5 reference solutions. So we'll calculate the other 4. Now, when you make your graph, of course, you're going to have your absorbencies measured. And so what you'll do is you'll plot your absorbance on the y-axis, and you'll plot your concentrations that you just calculated on the x-axis, and you'll form this nice calibration curve. Now, here's the thing. The trick is making sure that you do this very correctly when you make your measurements. And if you don't do that correctly, what will end up happening is your calibration curve will be wonky. It'll not be straight and linear like you want it to be. Now, the end goal here again is to solve for the equilibrium constant. This is the first part of this, and so we need our calibration curve. Now, from the calibration curve, you're going to figure out the linear regression equation, y equals mx plus b. Now, keep in mind that you're going to be doing this at home, and so you'll be working on Excel. All right, so now as we move on into the test solution, so again, the goal is to, first part is to figure out what the reference solutions are, and then we're going to start working with our test solutions. All right, so again, we've talked about part 1, which is dealing with the reference solutions to make your calibration curve. Now we're going to look at part 2 and what we use the test solutions for. So what we'll do for the test solutions is this goes back to understanding, how we take the test solutions to figure out the equilibrium constant. Now this goes back to the ice chart in the very, very beginning of this chapter that we've been working through. And so one of the first things we need to do is we need to figure out what the initial concentrations are for both parts. Now, the difference is from the test solution versus the reference is, in the reference solutions, we used the linear reagent for the SCN. Now, the difference here in the test solution is the concentration for the iron plus 3 and the SCN minus are the same. So there's no linear reactant here for this part, and so that means that you have to do something a little different. We can't just say, oh, well, this is the concentration for the equilibrium for the iron thiocyanate. That's not how it works. So we're going to have to use the ice chart to figure that out. Now, the nice thing about this part is that once we've calculated our equilibrium, our initial concentration. So the way we do this is you take the information you find from the table 2, and so for the iron plus 3, you'll see that it has 5 milliliters of the Fe plus 3, and you have 1 milliliter of the SCN minus. Now, in the beginning, I told you that we're going to keep the volume constant at 10 mils. In fact, that's the way it's throughout the entire lab. That way it's simple. So again, we go back to our M1V1 equals M2V2, and you solve for the initial concentrations for these two. Now, using the ice chart, in this particular case, since you have 5 test solutions, you're going to have to do this 5 different times, okay? So you're going to calculate the initial concentration for these 2 here. We do not know what this is. It's obviously zeroed initially, but what we do know is that from the linear regression equation, we use the linear regression equation to solve for x. Now, knowing that this value here, this FeSCN plus 2, is just a 1-to-1-to-1 ratio, that means that this change, this plus x, is the value that you gain from the linear regression equation, okay? And so in class, the way you would work this out is that you would do this from the calculation. Well, we don't have to worry about that this time because our x is determined from the linear regression equation. In fact, if you look at this chart here, what we're going to do is we're going to fill this in, and we're going to use this chart to ultimately figure out what the equilibrium constant for each of these parts are. And since there are 5 of those, we'll have 5 different values. Hopefully they'll be the same though. So this equilibrium constant here comes from, this equilibrium concentration, I should say, comes from the value that you determined from your linear regression equation. Okay? So you have to use that y equals mx plus b to do this. So again, the way this works is you're solving for x. You know what your y is because in the experiment you measured the absorbance for each of the test solutions. And those absorbances are going to be representing what you use for y. And then obviously from the linear regression equation you're going to solve for m and b using Excel. All right. So our goal is to solve for x. You'll do that not once, not twice, but 5 different times. And those x values that you calculate for each of the test solutions goes here. So you have x1, x2, 3, 4, and 5. Now, again, that does not tell you the equilibrium concentrations for the iron plus 3 and the SEN minus. The way you determine those is by using the ice chart here. Okay. So again, we talked about how you calculate the initial concentrations for both of those in the iron plus 3 and the SEN using table 2. You'll notice that the iron plus 3 remains constant at 5 mils. So once you know that, you know the initial concentration for all 5 of those test solutions. But the SEN is going to change. It goes from 1 to 2 to 3 to 4 to 5. And so you'll have to recalculate the SEN minus the initial concentration 5 times. Okay, we've already done it once for you, so you need to do it 4 more times. So now again, going back to the ice chart, so you plug those initial concentrations in here. So now you know what the value for x is because you calculated it from the linear regression equation. So what you need to do here is you'll plug this x back in here. So remember that this is 1.0 times 10 to the minus 3 minus x, and then this will be 2.0 times 10 to the minus 4 minus x here. So the x gets plugged in here. Whatever you determine from that subtraction goes into the chart here. Okay? So now once you've determined the equilibrium concentration for all 3 parts, that's when you go back to the equilibrium expression we saw in the beginning. And I'm not going to pan over there, but it's on the other side. You saw it from the very beginning. You plug that in and you solve for the equilibrium constant. Now you'll do that 5 times again. So you'll have 5 ice charts. You'll have each of these. They, theoretically speaking, they should not be exactly the same because your value for x should change in each of those experiments because you have 5 different absorbance values. So these should never be the same. All right. Now when you calculate your equilibrium constant, now that should be theoretically the same, but we know with experimental error you're going to have some differences in there. So now what we're going to do here is that once you have solved for all 5 of those equilibrium constants, you're going to then average those constants out. And so once you average those constants out, you'll figure out the standard deviation and ultimately your percent RSD. Now, if you look in the very end of the appendix, you'll find the section where I show you examples how to do the statistic calculations. And so I want you to apply those rules here in terms of this. Now, keep in mind that this is a formal lab report, so in your discussion section for the report, you will use your statistics to talk about how well the experiment went for you. If you find that your percent RSD is greater than 20%, then you probably got some issues going on and you'll want to evaluate what may have caused those issues. There's a lot of different things, variables that can cause this, but one of the most important details for you guys in this lab is to make sure that you use clean glassware and you're measuring to the bottom of the meniscus each time you measure a volume. That's a very important detail there. So again, if you guys have any questions, just shoot me an email and then I'll see y'all soon in the lab. Thanks.